Okay, we are rolling. So yeah, this is week 2, lecture 2. And we're going to continue on our journey looking at the application layer. Essentially, today pretty much all we are going to do is mostly look at the web and take a very web as in HTTP really. That's the application layer protocol of the web. The web, of course, involves a lot more things beyond just HTTP, but of course, our focus will be on HTTP. And then I'll very briefly touch on email. As you'll see, email is a fairly simple application, and particularly given that we spend a lot of time looking at HTTP, you'll notice there are some similarities with how email and particularly SMTP works. So we'll not spend as much time looking at email simply because it's fairly straightforward. So the origins of the web actually go back to this person here that you see on the screen, Tim Berners-Lee. He was working at CERN. You might know of CERN, so that's where they do all the particle accelerator experiments. It's buried underground at the border of France and Switzerland. And of course, so there's a bunch of physicists working there. So what Tim Berners-Lee was doing was trying to connect all of their documents together, essentially, right? So the physicists, they were producing all sorts of documents, and Tim Berners-Lee's task was to create essentially a way to link all of these documents together. And that's where he came up with this concept of the hypertext transport protocol, and that's where the name HTTP comes about. So the first implementation was way back in the 1990s. And of course, at that time, this was still a niche project, but eventually it got picked up quite widely. And through the early 1990s, there were a few iterations in terms of the various versions. And you'll notice then there was a huge gap actually, and we've only moved on to the next version recently. And in fact, a third version is actually on the horizon as well. So you could actually check out the first web page ever created. Of course, it's not very exciting. As you see here, it's just a fairly simplistic text-based web page. It's just been kept here for as a history record, really. And if you think about it, web is really the key application, right? So this is sort of every year they release this, sort of giving you some context on how much activity people are, what sort of applications people use, and how much activity they generate on the internet. Now, of course, all of this is not necessarily using the web, but a large fraction of this is, right? I mean, YouTube, for example, a lot of YouTube gets streamed over the web, Facebook, LinkedIn, Netflix also uses the web, actually, as you'll see next week when we talk about CDNs, and so on and so forth, right? So just, I mean, just look at these numbers. They're just humongous, right? I mean, there's so much content being generated these days. It's virtually impossible for us to keep up. So in terms of the web, what exactly does it entail? So essentially, when you're accessing any web content, it's a collection of objects. And these objects are, of course, hosted on web servers. And then we have the clients, which are implemented in the browsers who request these objects. An object can be really anything, right? It can be, of course, like a classical index.html file, like a basic HTML page. It could be images, it could be applets, it could be scripts, audio files, video files. I mean, anything really, right? And the way to actually identify any object is through this URL, as you see here. So this contains the name of the actual host that's hosting this object, and then the directory path within that particular host where this object is actually located, right? So URL stands for Uniform Resource Locator. And truly speaking, this is not just specific to HTTP. This can be used by a variety of protocols. It's a fairly uniform way to identify things on the web, on the internet, I should say, not just the web. So up here you have, of course, the protocol, and then you have the name of the host. The port number is optional, as we'll see later. The port number, for example, for HTTP is 80, so you don't have to specify this. If it's HTTPS, then it's 443. So these are sort of well-known ports which don't need to be specified. And then, of course, you have the actual path where the resource is located. Right. So the protocol would, of course, be, in our context of the web, it's HTTP, or HTTPS, but it can also be other protocols. The name of the host is the identifier that we use for the website. Now, we'll be looking at how this gets converted to an IP address next week. But really, the computer actually needs to know the IP address. As humans, we are more comfortable remembering host names, right? It would be very difficult for us to actually remember IP addresses. Like, for example, google.com, that's easy to remember, but the IP address of Google is not so easy to remember. So we humans tend to use host names, but these do need to get mapped to IP addresses. And we'll look at how that gets done next week. The port I already mentioned, and then the directory path, the resource, right? So if you look at HTTP, there's not really a lot here. It's a fairly very simple protocol, right? Its role is to transfer web objects from the server to the client. So it uses this very simple request response model, right? So the client, which is the browser, requests the object using HTTP, and then the server responds back with a HTTP response message that contains the objects. And this keeps happening till the web page is fetched, and then the user might move on to another page, and so on and so forth, right? Now, sometimes if you're requesting for something dynamic, the server may also need to contact another server to generate the content you're asking. So let's say, I don't know, if you're looking at live stock market indexes, then this server might have to poll another server which is hosting that information, extract whatever is needed, and then send back. So that certainly can happen, but that's kind of invisible to you, right, as a requester. And of course, the HTTP protocol itself is open source. It means that anyone can look at the spec, anyone can write their own browser program. So if you really wanted to, you could write an HTTP client. Mind you, the browser does a lot more things than just implement HTTP. It does all the rendering for you. It may interface with plugins. It will manage your password. So all that is not necessarily part of HTTP. So of course, a browser is doing many more things beyond just implementing the client of HTTP, right? And then, of course, you have the server software, which is distinct. And again, there are various instantiations of this, just like there are various instantiations of browsers, like you have Chrome, Firefox, Safari, you name it. Similarly, you have different kinds of web server software. And the beauty there is HTTP being open source. It means anyone can really look at that code, design their own client. Anyone can look at the code and design their server. And if they've properly followed the spec, these two programs should be able to communicate with each other. In fact, in your not next lab, but I think the third lab, you will be implementing a very simple web browser, very simplistic, right? So you'll see that it's fairly straightforward to do that. HTTP uses TCP. We discussed this last week, last lecture. And the reason obviously is because when we are requesting web objects, we want to make sure that the entire object is delivered. We can't have bits and pieces missing. And since TCP gives us reliable data delivery, it makes sense for HTTP then to use TCP. So it doesn't have to deal with the headache of managing lost packets and stuff like that, which TCP takes care of, right? So before this process can actually happen, before the HTTP request can be sent, the client would set up a TCP connection with the browser. And once the TCP connection is set up, then the requests and responses would sort of get transmitted over that. So HTTP, of course, it's an application layer message. So there are different types of messages, request and responses really. And once all that exchange happens, then the connection can be closed. There's a question here. Let me take that by Patrick. Is domain same as host name? Yeah, I mean, there are some minor intricacies there, but for the sake of our discussion today, we'll just assume the domain is the same as the host name. We'll talk a bit more about host names next week when we go into DNS. So HTTP inherently is stateless, which means the protocol itself was designed in a way where the server and client don't need to keep state about each other. This is particularly important for the server because remember, a web server might be servicing hundreds, thousands, maybe tens of thousands of requests, right? So requiring the server to maintain state about each client it's talking to would create a lot of work. So that's the reason the protocol inherently was designed to not maintain any state. So this means that if you ask for, let's say you're a client, you ask for an object, the server serves you that object. And then if you ask for that object again, the server is not going to come back and say, hey, you already asked for that object before, right? Because it's not actually keeping track of your previous history. And of course, having this stateless design allows the protocol to be less complex, which means it doesn't have to worry about what happens if, say, the client crashes or the server crashes and there's inconsistencies in the state, right? So all these factors make the protocols complex if you want to design a stateful protocol. So that's the reason HTTP is inherently stateless. One of you, Dharam, has asked, what about, so that is why client-side cookies are required. Yes, I'll come back. I'll come to the point of cookies. Just give me a few minutes. But yeah, that's a good point. That sure, HTTP inherently is stateless, but as we have discovered, once everyone started using the web to do various sorts of interesting things, a need arose to have some state, because without that state, it becomes very difficult to do a lot of things that we might want to do on the web, right? So for that, cookies were developed, and that's something we'll just touch upon in just the next few minutes. Okay, so what are the messages? They're fairly straightforward, request response. In fact, these are ASCII. So the actual messages themselves are human readable, right? So this kind of shows you the age of HTTP. I mean, I don't think if HTTP was designed today, they would actually go with this ASCII option, because for ASCII is not really efficient. You can pack in a lot more data if you don't use ASCII in the same amount of bits, right? So, but in any case, that's what that's how the protocol was designed, and that's how it is. So the first line is kind of important. It is the request line in this request message. So the first word here is basically the command, and there are a few options which we'll look at, but the most commonly used one is obviously get, which are requesting for an object. Then you have the object, essentially with the file path that the object is hosted in, the version of HTTP. And at the end here, you have this carriage return line feed. So that implies this is the end of that request line. And then there's a bunch of header lines. Now, these are strictly optional, and how many you have. And in fact, even the ordering is optional, right? So it's not like you always have a fixed number of headers, but these, some of the ones you see here are the typically most commonly one used. So the host is the actual host name from which this object is actually being served. The user agent is, of course, the browser that's being used, language, encoding, and so on and so forth, right? This implies the TCP connection will be kept alive. We'll come back to this point. But at the end of these headers, you'll notice there's an extra carriage return line feed to imply that's the end of the headers. And in fact, in a GET request, you won't have anything in the actual body. So it's just the request line, the headers, and that's it. Right? Now, let me ask you a question before we go back. I probably should have made this a proper question, but can one of you think of why we might want to use, why should we include the host name? I mean, if you looked at the previous slide, we said that, okay, a TCP connection is established between the browser and the server that's hosting the host name that we're fetching the object from. And then once the connection is established, you can send the GET request, right? So why do we now need to include the host name if we have already set up a connection with the server that's hosting that host name? Anyone has any thoughts? We're jumping ahead a little bit, but okay, there's a bunch of answers here, and Cameron actually has the correct answer. You've probably, in the sense you're pointing in the right direction. The exact wording you've used is probably not precise, but remember, these days, right, a lot of websites are hosted on, so they're outsourced, right? So they are hosted in data centers. So for example, my website, I don't host it myself. I use DigitalOcean, right? Many of you might have set up websites using, I don't know, GoDaddy or whatever, right? So effectively, that means my web page is actually hosted on the DigitalOcean server. Now, obviously, DigitalOcean doesn't just host my web page; it will host thousands of other domains, right? So my domain is salilkanere.net, but obviously DigitalOcean is not just hosting my domain; it's hosting, I don't know, 10,000 or whatever, millions of domains, right? So let's say you are accessing my web page. So you send a GET request for my homepage, right? The index page. Now, how does DigitalOcean know which index page to serve you? It's hosting 10,000 index pages, right? Because it's servicing 10,000 domains. So that's the reason it is kind of important that the actual host name is also included. So when you're accessing my web page, you would put down salilkanere.net here. I mean, by you, I mean, I don't mean you as person, but your browser would do that. And then you would be requesting the index page for my domain. So that's the reason we include that, because almost all content these days is hosted using one of these platforms where multiple domains are actually hosted, not just one, right? There's a question, how does the request message know to get to DigitalOcean in the first place? Yeah, so that's where DNS comes into play, Tim, and that's what we'll look at next week. That my domain, salilkanere.net, we need to map it to the IP address of DigitalOcean, right? So imagine there's like a yellow pages on the internet. So we go and check the yellow pages, say, hey, what is the IP address of salilkanere.net? So imagine you're sending this query to this yellow pages black box, and that yellow page black box spits out, here's the IP address of DigitalOcean that's hosting my particular website, right? So all that process has to happen before we set up the TCP connection, and then we send out the GET request. And this yellow pages I was referring to is precisely what DNS does, right? Yes, that So there's a question, if we host it locally, do we need to include hostname? So typically most browsers would always include the hostname, because how do they know, right? How the hosting is arranged, your browser has no clue. So it will always include the hostname. Sometimes it might not be needed. If this is dedicated, if you have a dedicated IP address that's only hosting this, then this may not be required, right, in that case. But how would the browser know that? So this is it's very typical to include the hostname in the header line. Tim is asking, but does that happen outside? Yes, so DNS happens first. The mapping between the IP address, the hostname and the IP address happens first. Then the TCP connection gets set up, and then the GET request is sent, right? So by the time we get to the point of sending the GET request, we've already established a TCP connection with the correct server, right? The request message would be treated as a packet with its own packet headers to orient it, right? Yeah, so that's something we'll look at a little later, right? So that GET request gets put inside a TCP segment, which gets put inside a IP datagram. We talked about this encapsulation in the previous lecture, right? So one of those headers will add the information that's needed to direct the packet towards the destination. So right now we are still at the top layer, right? So we are abstracting over everything below. So this is just a illustration of the header, which is just a nicer way to illustrate it. Basically, you have the method, white space, the URL, white space, the version, carriage return line feed, and then a bunch of headers, and then the body. And in fact, the response message has the exact same format. So normally in requests, you don't have anything here, except if it's a put request, which we'll look at later, and if it's a post request. But for GET requests, you don't really have anything in the body. The response format is exactly the same. Instead of the method, there's a code here, which we'll look at later. There's a bunch of headers and then the actual object that's being requested, right? So the request methods are of the following type. So the GET method is obviously the one that's most used. Now, sometimes you might have filled in various web forms, right? So you fill in certain fields and then you hit submit, and then all the data that you've filled in gets sent to the server. So there are two ways to do that. The normal way is through the post method. So this is typically when you have a lot of fields in that form, right? So in that case, all the things you enter in that form gets put inside here and then sent to the server, who can then retrieve it. Sometimes you might notice when you're doing web searches, you'll notice the data you're searching for actually gets added into the URL itself. So let me just do a quick illustration. Let me go to Google. What do you want to search for? Right. So if you look at the bar here, you'll notice that it's actually put in the word I searched for directly in the URL, right? So rather than use the post method, the data I entered just got sent through the GET method itself. So that's another way to actually send data to the server. There's another method called the head method. This is more used for diagnostics. So when you're setting up a server, when you're designing, say, your own web server, you might just want to check the headers. And in that case, you might just send what's called a head method, where you're only requesting a header, not the actual object, right? So this is just for diagnostic purposes. And then these days you can also upload stuff, right? So when you're uploading stuff through your browser, say uploading a file or something like that, that gets sent across using a put method, where the file goes and sits in the body of the put method in this case, right? So Yeah, moving on now to the response message. As I hinted earlier, the format is very similar. So we start off with the there's a couple of questions. Is patch and put method the same? I think patch is again used for probably some diagnostic. I forget exactly the purpose of patch, Patrick. Barry, what is the difference between post and put? So post is mainly when you're filling in stuff using forms, right? When you have a web form and you need to fill in stuff and send it. Put is where you're just uploading a object, right? So if you're uploading pictures and stuff like that to Facebook through your browser, that gets sent using put. Okay, so the response message looks similar. It starts with the version, and then there's this code and a little bit of text explaining what this code means. So normally when you're requesting an object and you get the correct response, you would encounter this. Then of course, there's the date when this object was created, the server software, what kind of software is being used for the server. This will have some relevance later when we talk of caching, but this basically is the time when this object was actually created. So notice this need not be the same as this. This is the time the response was created, but the original object could have been created earlier, right? E-tag is essentially a hash of the content that's being sent. And again, I'll come back to the need for this a little later. And then there's a few other headers which we won't spend a lot of time on, but notice at the end, there's again a /r and /n, and then there's the actual data, right? So there's a bunch of response status codes out there. These are the most common ones. That there's a lot more. So this is the most common one. These have to do with redirection. So all the 300 ones, which we'll look at briefly when we talk about CDNs. But this is a way to redirect your query to another server if it's not being hosted on that server where you requested the object from. And then some of the 400 ones are all error messages essentially. Right. And then, yeah, there's this, and there's a few crazy ones. I think there's one called I'm not a teapot. I think that's just a joke someone played when designing the standard, but it's actually there. It's part of the standard. I forget the exact code for that. Right. There's a question. So the post method, the message sits in certain format. I mean, it would, I guess it probably takes stuff from the form. I haven't looked closely at the exact format, but all the data that you enter gets basically put inside that, right? So yeah, in terms of 404 and 403, there are certain differences. You can look up all the error codes. Yeah, I think one of you has put the link. So there are some intricacies there. We of course won't be discussing all that here. You can read that up, but there are certain differences. So generally the 400 family is for errors, 300 family is for redirection, right? 505, I would see if I fired up Netscape, maybe, I don't know, possibly. Okay, so HTTP is all text. And again, the origins go back to the 1990s. So at that time, they thought it would be nice to have a protocol which humans could read. So it makes the protocol simpler, but then you'll notice this means the length can be variable because the length of the host actually depends on how many the header fields, right? And in fact, even that first line depends on the actual length of the ASCII value there, the text there. So it's not a fixed size anymore. And certainly it's not efficient, right? So for example, if you wanted to send a number like this, if you send it as ASCII, or basically using 8 bytes, one for each digit, whereas if you used a 4-byte integer, you could send the same thing, right? So you're basically saving 50% if you chose to use integers rather than sending stuff like that. So certainly it's not very efficient. The other thing is when you're writing code, it gets clunky because you need to do string parsing and processing. Now, of course, there are libraries to do that, but someone had to design those libraries to begin with, right? So it's a bit clunky to have to sort of extract stuff that's text, right? And then anything that's not in text needs to be encoded as well, right? Okay. So that was a quick high-level view of HTTP. Now what we'll do is we'll move to the question that was raised earlier about keeping state, right? So fine, HTTP is stateless. And the reason for having that is kind of illustrated here, right? So if you're doing stuff like that, where you're changing a data value, and then if something happens, for example, if the connection crashes somewhere here, then we have a situation where there is inconsistency between what the client sees and what the server sees, right? So we certainly have problems. So stateful, designing anything stateful is much more complex than stateless, and that's the reason HTTP was designed as a stateless protocol, because then there's no issue of recovery or anything like that. Each HTTP request is just independent. There are absolutely no dependencies, right? So cookies then. Now that was fine till people started using the web for implementing all sorts of cool things, right? So imagine you, when you go to Amazon, you want to browse through the Amazon, whatever products they have, and you want to create a shopping cart, right? Which means if you're on one page, you like something, you add it to your cart, then you move to a different page, which means now the server has to keep some state, right? That on this page you bought this, now you're moving to a second page, you bought something else. Then the server might want to remember your account because all of that gets added to your shopping cart, your basically address, payment details, all of that is being stored. So essentially it's obvious that now to do all sorts of complex things over the web like that, the server, and in fact, even the client might need to maintain some state, right? So we certainly need to overlay some state maintenance on top of the stateless HTTP protocol if we want to actually keep state. And that's where the idea of cookies came about, right? So the way to implement this is not very difficult. Essentially, there's some extra header fields that are included in the response and request message, which carry some of that state to convey essentially the user that's being referred to the server. And then there's a state maintained both on the client side in what's called a cookie file, which is integrated with the browser, and then on the back end at the actual website that's hosting the content, right? So the way this works is, let me actually just illustrate this using the picture. This is basically just verbalizing what's shown on the next slide. So imagine here we have this particular client. Let's say it's me. This is my browser. And my browser keeps a cookie file, right? And you'll notice here there's a cookie created for eBay. And let's say now I'm accessing a different website, right? And this is the first time I'm actually accessing Amazon, right? So I visit Amazon, I send this HTTP request. The Amazon server creates a unique identifier for me and adds it into this backend state database. And it sends me this identifier, which is essentially referred to as a cookie. And this is done through this special header field that's part of that header. When my browser receives it, the 8 got eaten up. Sorry, I'll fix that up in the slide. So my browser will now add this cookie into my cookie file. And from that point on, anytime I'm communicating with the Amazon server, the browser will include that cookie in the header, right? So now the server knows this person is whatever. I mean, the server doesn't necessarily need to know it is me as such. Certain websites might, but certain websites may not care. But in any case, there's certain state information that's maintained here, right, which matches with this. So now the server knows, okay, this is this user. So maybe the next time I'm visiting this, if I've bought some stuff from Amazon before, they may see my record, my history, and when I visit Amazon the next time, they may show me, recommend me certain items, and so on and so forth, right? So yeah, basically that's what's shown here, right? 1 week later, assuming I've still kept my cookie and I visit, then that cookie would be included, right? Because my browser knows I'm sending a GET request to Amazon. So it will then check the cookie file and see that I already have a cookie for Amazon. So it will include that in the HTTP GET request, right? Yeah, so that essentially allows the server to maintain state about the client, right? And you can do, of course, a lot of interesting things. You can build shopping carts, recommendations. I mean, anything really that you think of requires states. And in fact, a lot of things we do actually today do require state, right? That's just how the web is being used today. Now, of course, remember this is all, there's a lot of intricacies to this. So some of the questions you're asking, I don't think we'll be able to get to that. So there's a question, how does it know you are new and don't have a cookie? Well, as I noted here, anytime you visit a website, right, your browser will check if you have a cookie for that web domain, the host name, and if so, it will include that, right? So as long as this cookie file is not deleted, in which case if your cookies are lost, then obviously it can't do that. But assuming it's not, then it does get included. Can the user alter the cookie data? Possibly, but then the question is, what would you alter it to? I mean, you can certainly delete your cookies. In fact, after this, I'll just show you a quick demo of how this all works. To impersonate someone, you could, but you would need to know their cookie, right? Their specific cookie information, which is a bit hard to know. You would need access to their cookie file. So that might be a little more challenging, right? Does only one cookie get made? So yeah, that's where there are some intricacies on that. There are different types of cookies and all that. So I don't think I'll be able to get into those finer details. From our perspective, let's just assume there's just one cookie, right? Keeps things simple. Can websites read all your cookies for other websites? No, they shouldn't be, right? Because your browser will only send the cookie for that domain. So you're not sending the entire cookie file to someone, right? How does information such as passwords linked to an account get transferred? Well, that's a little different. I mean, some of that functionality is implemented in your browser, right? So your browser might store your password. I mean, if you use Chrome, for example, Chrome has its own password management tool, right? That's overlaid on top of it. So in that case, that is not inherent to HTTP as such. Or you might be using a password manager like LastPass, where you have this widget that you can add into your browser. So that's something that's overlaid essentially. And when you're presented with the login page, the browser will automatically pull that and send it, right? So it's not part of the HTTP protocol or even cookies as such, right? Is it safe to use cookies? Well, the thing is, yes, there are lots of bad. In fact, let me just move on. I'll talk about some potential issues with cooking. But the thing is, if you disable cookies, there's a not. I mean, it's very difficult to do any of this, right? If you completely disable cookies and are not willing to use cookies, then you won't be able to actually use a lot of information, right? What is user session state? Well, that will depend on what information this website is storing about you, right? So if it's Amazon, it might be storing a lot of things. If it's some other website, it may not need to store all that information. So it really depends what information you've given them, which allows them to link this to your state. So it's hard for me to just tell you what that state is. It's very specific to how the information that the backend is actually keeping about you. So one of the problems with cookies is it allows some of these entities to actually track your web habits, right? And there's this whole third-party cookies madness that has emerged, essentially, whereby these third parties can actually, particularly these are ad networks, right? So a lot of these, I mean, there's no direct, they're not necessarily after you as such or your specific information. What they're trying to do is profile you, right? So they want to know what sort of websites you visit, what are your interests, so that they can serve you ads that might be more suited to your profile, right? So I'm sure you've all seen this, right? You start seeing ads on Facebook, which suddenly I don't know, you went to this particular movie the previous day, you bought the tickets online, and then when you go to Facebook, they start showing you some relevant merchandise for that movie or whatever, right? So stuff like that, I'm sure you've encountered on the web. And the primary reason that they can do this is because they're tracking your online behavior, essentially. So I'll give you a very simplistic example of how this might happen in the next slides, right? So this is a very simple example of this. So imagine there's this third party called DoubleClick, which is essentially an ad provider. So they're hosting ads for various companies, and their sole purpose is to try to entice you to click an ad, right? Why do they show you ads? In the hope that you click through, right? You actually click on the ad, you go to that website, and if you actually buy the product, that's a big win for these providers, right? So in the olden days, I don't know, how old, I know some of you are very young, but I don't know if you have seen websites where they add these humongous ad banners. Some websites still do, right? So imagine you have websites where you have those sort of ad banners at the top saying, hey, this is an advertisement for this, right? So let's say this is me. I visit this particular website, right? So my browser sends a GET request for this website. Now note that on this website, there's a image that's stored. Now this image is not stored on this server that's hosting my website. This image is actually stored on the DoubleClick server, right? So when my browser goes and fetches the index page, it will get all these other URLs for all the other objects on that page. And one of those URLs will actually point to the DoubleClick server. So to actually fetch this banner, my browser has to set up a TCP connection with the DoubleClick server, then go and obtain this particular object, the banner from the DoubleClick server, right? And imagine this is the first time my browser has visited the DoubleClick server. So what does DoubleClick do? DoubleClick now creates a cookie for me, right? Let's say it's 3445, right? Now let's say I move on to another website, right? Yeah, it does. So there's a question, even if we don't click on the banner. Yeah, because this is just displaying the object, right? I haven't clicked on the banner, right? This is just for me to see the actual banner, right? Then let's say I go to another website, right? And imagine this website is also hosting this banner, and that banner is again hosted on DoubleClick server, right? A banner is just an image, Barry. So then I go and click that particular, I go and download that particular website. And again, since the image here is hosted on the DoubleClick server, my browser would then set up a TCP connection with the DoubleClick server. Now notice there's already a cookie created. So my browser is going to include that cookie when it sends this request for this banner. And now DoubleClick knows that I visited website A, I visited website B, then I go to website C, right? There's another banner here hosted by DoubleClick. So now DoubleClick knows I visited website C, and this continues on and on and on, right? So essentially, by having these images hosted on these various websites, DoubleClick is now able to essentially track all my web activity, right? And in fact, these don't even need to be visible to you. So they sneak in actually single pixels, right? So rather than hosting something very visible to you, they may just put in 1 pixel within that particular website. So as a user, you don't even see that, right? So they are sort of invisibly tracking your web activity, right? So in fact, let me illustrate that very quickly to you. Right, so this is Firefox. I just cleared out my, so this is my cookie file, right? So as you see here, it's completely empty. I've cleaned out everything. And here I've selected the standard settings. So what this means is this particular browser is not going to allow this cross-site tracking, which I just talked about, right? And stuff like that. So it's not going to allow third-party entities to track, to establish cookies, right? So with this standard setting, let's see what happens, right? Let me just pick, I don't know, CNN.com, right? So let's now see what cookies are actually created. I think it needs a bit of refreshing somehow. Yeah, okay. So these are the normal cookies that were created using this standard process. So already you see, okay, CNN.com, 41 cookies, as one of you asked how many cookies, right? So there can be actually many. There's a cookie for Google and some random stuff. I have no clue what these are, right? So you already see that even with this standard security setting, a lot of cookies were created, right? Which I have no clue. I mean, I visited CNN and I've got now these 5-6 extra cookies, which are not obvious from here, right? I mean, Google is probably because of this search, because they're hosting this search, right? So that kind of makes sense. Some of the other ones, see, this is this sneaky banner I was talking about. I mean, even to this day, we have these sneaky banners everywhere. Now, it's very likely this has not created a cookie because I've used the standard, which is sort of secure setting, right? Now, let me show you what happens if we don't use the standard setting, right? So let me remove, save, right? So my cookies are now cleared out, as you can see. Now let me go to custom and let me enable all cookies, right? So let's just throw privacy out of the door. And let's say I'm allowing all sorts of cookies to be now created, right? And now let's go back to the same web page. It takes, I don't know why, it needs a bit of refresh for some reason. Okay. So how many did we have before? 5 or 6? And how many do we have now? 20, 30? I have no clue. So you clearly see, right, that there's so many third-party cookies here. And obviously none of this is quite visible, right? I mean, where do I see all this? I have no clue, right? That's probably one. That's probably another one. In fact, you see here, if you look at my status bar at the bottom, you'll see this is doubleclick.net. In fact, Google has bought doubleclick.net, right? So you see this at the bottom there, right? So you clearly see this is a big problem. And so that's the reason the general advice for all of you is to not sort of throw privacy out of the door, at least to go with the standard setting. I mean, you could use strict settings, but then sometimes it may create some problems with accessing content. So you can have a play around with some of this with your browser and have a feel for what all this means, right? So what questions do we have? How is it possible that I get ads for something specific after only talking about it with friends or family? That I'm not so sure, Dimitri, unless they're actually listening in on you. I mean, some of us do not remember necessarily what we've browsed. So I doubt people are actually listening to you, but it's very likely through something to do with the web where you access that information and they've found that out and they're now serving you ads that sort of match up your interests. There's a question. So we visit a site, it makes us make another request to the site hosting the banner. Yeah, exactly, right? So that's what I showed you on this slide, that a lot of this content is not in that example. I visited CNN. So a lot of the content on that page is actually not hosted on this CNN server as such. It's hosted through some other servers, right? And then you visit those servers and then they create these cookies. Facebook pixel, yeah, exactly. So Facebook is quite notorious. They've put in these pixels everywhere pretty much, right? Are the cookies stored in blob storage? I'm not sure what blob storage is. It's basically some file, right, within that your browser can access. So it's some local storage on your machine. Does Chrome have the same features as Firefox? Yeah, I would think so. Most browsers these days have very similar features. They'll allow you to look at these cookies, have some control over it. So I would strongly encourage all of you to look at this and not ignore it, and be aware of what's happening, right? How does the client know which response goes where? You send multiple requests to the same hosts. Well, actually, I forgot to show you this. So let's actually look at, I mean, we looked at cookies, but let's look at when you're accessing a particular page, right? What's actually happening. So there's this extension I have. Where did it go? Oh yeah, here. Or you could, some browsers also have some developer tools, so you can use some of them. But this is now going to show you all the requests that are generated. So let me visit a very basic page. So let's say I visit the UNSW page, right? So I visited unsw.edu.au. As you see, there's a lot of content on here. So obviously each of this is a separate object. So there's tons of objects here. There'll be tons of scripts as well. So if you look at this sniffer, it's now going to show you all the, I think time goes upwards. So this is the first request that was sent. So you notice a GET request is being sent for UNSW. So these are the headers. Sorry, oops. It's probably not very clear, but if I click on this, you'll see it expands out at the bottom. So these are the request headers that are sent, as you see here, right? So this is for the base UNSW page, but you'll notice the actual website itself has so many objects. So the way this works is your browser first obtains the index page, the base page for it, UNSW, and then there'll be lots of other objects being hosted, right? So you saw here how many, there are like 50 plus objects hosted that make up that page. So each of those objects now needs to be separately requested, right? So this is another object that's being requested. That's some, I don't really know what these, so there's a lot of images here, as you can see, right? So each object has to be requested separately, right? Some of these, as you see here, are hosted in Google. There's something on the newsroom domain, YouTube, and so on and so forth. Largely, most of it is on the UNSW domain, but there's a few other stuff. There's some analytics which most websites would host to collect some data about the users and stuff like that, right? if you were using an ad blocker, would cookies still be created? Yeah, I mean, that's an interesting thing. So ad blockers will try to block some of these cookies. They may or may not succeed, right? So there's, again, all the controversy about ad blockers is if you pay, if the content provider pays the ad blocker enough money, they'll consider their website to be whitelisted and then allow those cookies to sneak through. So certainly having ad blockers is nice, but be aware that there are always financial aspects to that, right? So ad blockers may allow some cookies to sneak in because those companies are giving them money, basically, right? And then, yeah, some sites may block ad blockers completely. If they notice you're using ad blocker, they'll stop serving you content. So yeah, it's not an easy question to answer. I mean, that's where we'll leave it, right? So there's a lot of there are benefits to allowing people to track us, but then there's a lot of downsides as well. So it's a trade-off. And then the question is, how much of that are you willing? Where are you on that scale, right? Do you not want to use cookies at all? Well, then you're going to have difficulty buying stuff on Amazon, right? Okay, so I think let's keep moving. Okay, maybe not. No, this might actually be a good point to take a break. So let's have a quick break, and we'll come back in 5 minutes and then start looking at some performance aspects, right? Let me just pause the recording. Okay, so that's our funny meme for the day. Let's now get back to work. Okay, so let's now start looking at the performance aspects, right? As you saw from that quick demo I showed you, a typical web page will actually have several objects, right? So from the perspective of the web as an application, if you think about it, the page load time, the time it takes to actually view the entire page, is a very important metric, because they know that us users are very impatient. And so from a content provider's point of view, it is quite important that when someone clicks on a URL or types in, say, the host name, that they actually see the web page as soon as possible. So this is something that they do a lot of measurements on, and they're trying to optimize this latency, the page load time, as much as they can. And it really depends on a number of factors, right? So it of course depends on the content. If you have a very content heavy page, then obviously it's going to take a lot longer. It depends on the way these various objects are actually fetched. So this is where we'll spend a bit of time on particularly how HTTP has been designed to try to optimize this. The bandwidth and round trip time is not, I mean, this is just something more general, right? It's not something you can instantly control. Of course, we can keep designing better kinds of networks, increase bandwidth, reduce latency, and so on and so forth. There's of course the rendering time, as one of you pointed out, as well, but that's a little bit out of our discussion. So it's more about how you design the browser software so that you render this nicely as the objects come in, right? So yeah, from the perspective of the performance goals, of course, depend on the perspective. So from a user's perspective, of course, they want fast download, they want high availability, which means websites should always be available. From the content providers, well, of course, they want to keep users happy. So that's the same. But they also want to keep their costing low, right? I mean, of course, you could throw in a lot of money and get the content as close as possible, but then there are limits to how much money you're willing to throw at that, right? And then the network perspective, it's kind of secondary in that neither users nor content providers really care too much about the network, but it's still important, right? Because you want to make sure that the network is also not overloaded, because if the network gets overloaded, then it's obviously going to impact both the content provider and the user, right? So the ways to do this are as follows, and this is what we'll be precisely looking at in the rest of the lecture and even next week. So firstly, how do we improve the HTTP protocol itself to speed up the downloads? Then we'll be looking at caching, which is something that can help sort of get the content closer to the users. This certainly keeps the users happy because they can access the content faster. It ensures the content is available, and it also reduces the load on the network, right? And in a sense, caching, I mean, as you'll see later, web caches are actually deployed by the access ISPs. So it's not a cost that the content provider necessarily bears themselves, but it allows them in a way with not as much control as they would like, but still allows them to get the content as close to the users as possible. If they really want to have a greater say into how their content is sort of hosted and deployed, then they could leverage on hosting services, content distribution networks, and data centers. So there are third-party services which a content provider can access. They can pay them money, and these companies will then try to get their content as close as possible to the users. So there's this whole domain of content hosting or content distribution networks, which we'll briefly touch upon next week. So how do we improve the page load time? Well, you can, of course, try to optimize the size of the content, use smaller images, use compression, and so on and so forth. But that's kind of outside the scope of our course. So we won't be really looking at this. This is something we'll spend a bit of time on now, looking at how we can improve the HTTP process itself to fetch the objects faster. Then we'll be briefly looking at ways where caching can help, right? Particularly if there's the same content being fetched again and again, then we'll be looking at caching and how that can improve. And then finally, we take a CDN perspective and we look at how the content can be moved closer to the client itself, right? There's a question, is there a distinction between a web host and a CDN? Is a CDN merely a distributed network of web hosts? So yeah, I mean, those terminologies are a bit, it's hard to sort of precisely define those, right? I mean, a web host, so a web host is managing your basic hosting. They may not necessarily, I mean, they'll probably have some replication inbuilt into their hosting mechanisms, but they may not. CDNs are a bit more proactive in that they try to get your content as closer to the users. So they use a number of strategies beyond just hosting objects on multiple servers. So a CDN is probably a lot more powerful than just a basic web hosting provider, right? But again, those precise definitions are a bit variable. By bandwidth here, we really mean throughput, essentially the bandwidth, the capacity that the underlying network can provide, right? So as we saw already, a web page has multiple objects, right? So you have the base HTML file and then a bunch of images, JavaScripts, PHP scripts, you name it, CSS files, all that, right? So how do you retrieve all those objects? Well, a very naive way to do that is to fetch these objects one at a time. And in fact, you could sort of use a separate TCP connection for each object. So this is what's referred to as non-persistent HTTP, in that you set up a TCP connection, get one object, close the connection, and then if you have multiple objects, you keep repeating that process. And this was indeed the first version of HTTP, right? This is how the first version of HTTP worked. Now, again, going back to the timing diagram. So this is something you'll again see when we are discussing HTTP, where we'll kind of illustrate what's exactly happening, the message exchanges using pictures like this. And normally in pictures like this, we abstract over the entire network. So we are not sort of looking deeper into all the switches and so on and so forth. We just consider essentially the network as a whole. So remember what we talked about. We first establish a TCP connection. Now, as you'll see later, establishing a TCP connection actually requires a three-way process. But in these discussions, we'll abstract over that and we'll just assume it takes one round trip time to establish the TCP connection. A round trip time basically is the time to send a small packet from the client to the server and back. In these discussions, we assume the round trip time is fixed. In practice, of course, the round trip time can vary for each packet, right? Because there's, as we have already seen, queuing is highly variable in the internet. So it's not necessary that the RTT itself is fixed. So it takes one round trip time to establish the connection, one round trip time roughly to send the request and start to receive the first few bytes. And then typically objects are fairly large. I mean, they can be large. So depending on the size of the object, you might also need to consider the actual time to transmit the object itself, right? So this is a rough approximation of the total delay for one object. So 2 times the round trip time, one round trip time to set up the connection, one to send the request and start receiving the first bytes, and then the actual time to transmit the object, right? So there's a question, the round trip time is fixed. Well, I think I just mentioned that, right? That the RTT need not be fixed, but we'll assume it to be fixed in these abstractions. Are we going to get into HTTPS? So HTTPS is nothing but running HTTP on TLS, really. So it depends how much time we have. At the end of the course, if we have time, I'll cover TLS. If not, unfortunately, we'll have to let that go, right? So this was the first version of HTTP, right? So each object had to be fetched over a new TCP connection. So as you see here, you set up the connection, send the request, get the response, close the connection, set up a new connection. So obviously you see there are problems, right? Because if you're fetching all of these from the same server, why should you close the connection, right? It's kind of wasteful to having to keep wasting one round trip time for each object just to set up the connection, when you could just have set up the connection and used it for all the objects you're fetching, right? And then there are other issues to do with how TCP inherently works itself. So this is something we'll look at a little later. So for now, all you need to sort of remember is it's actually beneficial to have a long-lived TCP connection rather than just set up a connection, close it, and then open a new connection. Because TCP takes some time to figure out what is a good band, sort of the underlying bandwidth. So effectively determine a good sending rate, right? So if you have to keep setting up TCP connections, new connections all the time, you're kind of starting from scratch and not allowing TCP to actually discover the available bandwidth along the path, right? So another thing you could also do is send multiple requests, right? So rather than fetch objects sequentially, you could open up, you could sort of send them in parallel like that, right? So you could set up multiple connections rather than just set up one connection and send these requests in parallel. And then you start getting the responses. Now this, you may necessarily not maintain the order, because remember, again, we talked about how it's not necessary that all the packets take the same path through the internet, right? I mean, you would expect that too, but given that there are so much dynamics in the network, it may so happen that this request and response might go along one path, this might go along a slightly different path, and so on and so forth. So you do need to be aware that these responses may not come back in the same order, right? Now, let me ask you, sure, we can open as many parallel connections as we want, right? So imagine you had 50 objects. Like I showed you, the UNSW web page had a fair number of objects, right? So what if you set up 50 TCP connections with the server, one for each object? What do you think could be the potential downside of this? So if you could answer that, if you go to polev.com/ Salil, you should be able to try to be sort of concise in your responses. So let me give you a hint here. We are really focusing on from the perspective of the server. Yeah, I think some of you are answering correctly there. So they're on, if they are on the same server, you're overloading it, right? So effectively, if you, I mean, imagine the UNSW server. Imagine all of us go and access the UNSW server at the same time. And imagine each of our browser opens up 50 parallel connections, right? So if there are 100 of us accessing, then the UNSW server has to manage 100 times 50 TCP connections, right? So 5,000 connections for serving all of us, right? So that is one of the downsides of setting too many parallel connections. Most browsers will, though, they will typically always set up a few parallel connections, maybe not 50. That might be a bit too much, right? So moving on now, as we've kind of seen, it's kind of wasteful to keep opening new TCP connections. So the current version of HTTP will send out requests on the same TCP connection. So that's where the name persistent comes in. So you set up a TCP connection, keep it on till all the requests are sent and you receive the responses. And once you're done, then you can sort of close the TCP connections, right? And again, there are two ways you could do this. So the one here shown on the left is where you open the connection, but then you're still sending the request sequentially, right? So you send the first request, you get the first response, then you send the second request, you get the second response, third request, third response, and so on and so forth. Alternately, you could send, someone's mic is unmuted. Could you? Oops, how do I mute all? Okay. Yeah. So, yeah, so you could send out essentially the requests sequentially, right? One after the other, waiting for the objects to come back. Or you could actually, once you get the index page, you already know that how many objects you're going to fetch. You guys, could you please mute yourself? Someone is unmuted. Okay. So in that case, if you know how many objects are being requested, you could just send all the requests back to back and then hope that the responses will also come back to back, right? So this is what's referred to as pipelining, essentially, which is what the current or the previous version, I should say. I mean, we are sort of in the transition between 1.1 and 2.0, really. So this is what is currently used, essentially, right? Pipelining means you send multiple requests back to back like that, and then wait for the responses to come back to back. So this is how the timing diagram would look like, right? So imagine you have a website with one index page, which is the base page, and then 3 embedded objects. So you would need 1 round trip time to set up the connection, 1 round trip time to get the index page, right? Remember, unless you get, your browser gets the index page, the browser doesn't know how many objects there are, right? So you need to explicitly first get the index page. That will tell you how many other objects are in there. And then those requests can be sent in a pipeline manner. And then you receive the responses, right? So the total delay here would be 1 round trip time, 2 round trip times, and 3 round trip times effectively here, right? And then the time to transmit these 4 objects. So the total delay would be 3 RTT plus whatever is the time to transmit these objects individually, right? There's a question, if one of the responses is lost when pipelining, are all 3 sent again? No, not really, because, so remember here we are talking at the abstraction of the application layer, right? So each of these will now go and sit inside some TCP segments, which will sit inside some IPs, datagrams, and so on and so forth. And as you'll see, as we'll see in a couple of weeks, TCP implements certain mechanisms whereby if packets are lost, the sender will retransmit those packets. So all of that happens at the lower layer effectively, right? If those retransmissions have to be done, and that will be packet specific. So there's no relationship that if one of these gets lost, then the others need to be retransmitted. Why is there 3 RTT? Well, you probably can see it in this image. So 1 RTT, 2 RTT, and 3 RTT here, right? Is the time to transmit the request packet considered negligible? Yes, correct. So this request, the GET request itself, as you've seen, it's just very small, right? So that's the reason we kind of ignored this. Essentially, the thickness of this line is ignored. And even this, the connection setup, as you see, there is connection setup process itself is negligible. You can only see 2. Well, isn't that 1, 2, and then 1 more here, right? So yeah, what we can do is we can, as you have seen, we make HTTP maintain the TCP connection. So use persistence and then use pipelining, which allows us to speed up the process of downloading these objects. The next thing we can do is we can leverage caching, right? So caching is, of course, as a concept, it's also used in other contexts. So a good example could be in your computer hardware, right? So your computer, if you look at the motherboard, there'll be a local cache in there, which will store any data that your computer is referencing more frequently, right? So in that case, your CPU doesn't have to go and fetch it from the actual disk, but it could fetch it, or even the RAM, and it could fetch it directly from the cache, right? So the idea is kind of similar here in that if multiple people on the same network are watching, say, the same YouTube video or whatever, something that is substantially large in size, right? Typically, that's where caching really helps. Then you're better off when the first request goes out, you go and fetch the object and then you store it locally on a cache so that if anyone else on the network wants to access that object, it can then be serviced from the cache, right? So that's the basic idea, that you install this device, essentially a storage device that will store these objects, right? Now, of course, whether this works or not really depends on if there are repeat requests for the same object, right? So it only works if many people on the same network are accessing the same objects. If each user is accessing unique content, then caching will not work, right? And particularly now with a lot of dynamic content caching, the use of caching doesn't help there because that content might be specific to you, right? So like your Facebook page is different from my Facebook page, right? So there's no point sort of caching that because that will keep changing. However, particularly when it comes to video, there is a huge benefit because again, if you look at the way people access videos, there are a lot of popular videos which get a lots of views, right? So then it makes sense to cache those popular videos locally rather than have to go and fetch it from the origin servers. So there's a question. So does HTTP 1.1 or whatever it is for persistence mean request headers include some information that I'm going to be asking for this many objects, keep the connection open until you get all my requests? Yes, that is correct, Tim. If you go back to one of these earlier slides, you'll see there's a connection alive header flag in the HTTP request. So that's basically kept on, or alive, whatever, on or off. I forget the precise value, but that is indicated in the HTTP header. Is P2P caching possible? Yes, it could be. I mean, that's a bit trickier to do because to set up a cache, you need to direct all the clients, all the browsers to first go and request object from the cache, right? So if you're not using a central proxy, then how do you direct the queries? So that can be a bit more challenging, I think. So the idea of this cache is fairly simple. It's also sometimes referred to as a proxy server. So it sits between the clients and the origin servers, right? And all the clients in the network have to be configured in such a way that all GET requests will not get directly sort of sent to the origin servers. They would first go to the cache, and then the proxy server is going to send those requests on behalf of the clients, right? So it's something like that, where you send out the HTTP request, the proxy will first, of course, it will check if the object requested is stored locally. If not, it will go and fetch it from what's called the origin server, get the object, send it back, and at this time it's going to cache it locally, right? So that if someone else requests for that same object, it can then service it locally, which means you're saved a lot of delay because you don't need to go and fetch the object from the origin server, right? So effectively, as you saw there, the cache is acting both as a client and a server, right? So in its interaction with the clients, it's acting as a server. In its interaction with the origin server, it's acting as a client. Right? And caches are typically installed by all the access ISPs, right? So there's a question, how does caching work in HTTPS? Yes, with HTTPS, caching will not work necessarily because the content is encrypted, right? So then it's not possible to cache those objects, certainly. So as I said, the benefits of caching have kind of diminished a little bit, but one place where it certainly works is video, right? A lot of it, and particularly these days, a lot of video content is being exchanged, right? And then Tim is asking about the caching algorithm. So I think what you're referring to, Tim, is how do we clear out the caches, right? Because we can't store objects forever in the cache. So how do we remove old objects? And again, the same concepts of any caching. I mean, conceptually, it's still the same thing, right? So do you do first in, first out? Do you do last in, first out? Do you clear out objects that are not being requested much? So yeah, there's some heuristics that come into play, essentially. So, but we won't be touching on that here. So why web caching? Well, it reduces the response time, right? As you saw there, if the content can be serviced locally from the cache, it certainly saves the response time. So the users of the network are happier. The second benefit is it actually reduces the traffic on the institution's access link, right? As you saw in that previous slide. So in this instance, by having this cache, we only requested this object once, right? If we didn't have this cache, the request for this object from this client would have gone out, and then a request from this client would have gone out. So which means this ISP has to sort of, remember the ISP is always paying someone, right? So your local ISP is paying a higher tier ISP for connectivity to the internet. So each object that's fetched incurs some cost to your ISP, right? So by having this cache, your ISP has saved some money because that object was only requested once rather than twice, right? So in that sense, it's also a monetary benefit because you're reducing the traffic on the institution's access network. And you can sort of think as a cache as a sort of poor way to do some content distribution. I mean, as a content provider, you don't necessarily have control over these caches because the caches are managed by the access ISPs. So if I'm YouTube, I can't really control someone else's web server, web cache, but it certainly allows, I mean, these caches would be in a way caching some of YouTube's content, right? So it's a sort of indirect way for YouTube to get the content closer, right? But it would store duplicate data in proxy and origin server. That's fine, right? I mean, the benefit here is essentially for the client because it doesn't have to fetch the object from the server, right? It's stored once and that's it. It can be serviced to all the clients, right? From the client's perspective is IP for the domain change to the proxy server. So as I noted here, the GET request for the client is sent to the proxy server, right? So from the client's perspective, it's only sending a request here. Then the proxy server will sort of take care of it further along, right? Okay, so now let's look at a numerical example to sort of see the precise benefits of caching in terms of reducing the network delay, right? So let's use this particular example here. So let's imagine we are, this is say, I don't know, UNSW network or some institutional network, which has a capacity of 1 gigabits. This network is connected to the public internet over a 1.54 megabit access link. And then here we have the public internet and then we have the origin servers, right? And imagine we are using these sort of numbers. So the round trip time from the institutional router to the server is 2 seconds. So actually this should be this. So this delay is 2 seconds, right? So I'll fix this up. It's this router, not the institutional router. So the delay on the public internet is 2 seconds. We assume the web objects are all 100 kilobits. We assume on average, the network here is generating 15 requests. So if 15 requests are going out per second, we have 15 responses coming in per second, roughly. That's the assumption, right? So remember that each object is 100 kilobits. So 15 times 100 kilobits means the total incoming traffic here is going to be 1.5 megabits per second, right? Because 15 requests go out, 15 requests come in every second, right? So which means if you look at this network, we have a bit of a problem, right? Because if the total incoming traffic here is 1.5 and the total capacity is 1.54, you may remember earlier I had shown you that graph of queuing delays, right? So this was the queuing delay. This was the traffic intensity, if you recall. And in this case, the traffic intensity is 97%, right? So we saw that as we start to move from 0 to 1, right, the queuing delays start to increase. So if you're operating at 97% utilization, it's very likely the queuing delays are very, very high, right? Which means the latency on this part of the link is going to be very high. And if you look at the total delay, it's going to have 3 components, right? So there's some delay here on the institutional network, some delay on the access link, and some delay on the public internet, right? And we've assumed that the delay on the public internet is fixed, 2 seconds. The total delay here is going to be very low because the capacity of this network is 1.1 gigabits, right? So on this network, we are operating maybe somewhere here. So the delays are going to be very low. On this network, we are operating somewhere here. So the delays are going to be very large, right? So as you see here, the access link delay can be up to the order of a few minutes. The local area network delay is only a few microseconds. And then of course, this is fixed, right? So this becomes the bottleneck essentially. This is creating all sorts of problems on this network. Right? So how can caching help here? But before we get to caching, one other way to fix this problem could be to simply increase the capacity of that link, right? In other words, we try to reduce this utilization, and the way to do that is to increase the capacity of that link. So imagine we increase the capacity 100 times, right? So from 1.54, we go to 154, right? The rest of the settings exactly stay the same. So now the total incoming traffic is just 1.5 over, and if you sort of look at the intensity, it's going to be very low. So you're going to be operating again somewhere here in terms of the that graph I had shown you earlier. So which means now the access link utilization is just 1%, so very low. So the access link delay can now go, that 0.097, so it can go down to milliseconds, right? So effectively we've removed the problem. We've removed the bottleneck here by increasing the capacity of this link. Now, yes, this is certainly a solution, but the problem there is you're probably going to have to pay through your nose, right? Originally, you were paying for bandwidth that was 1.5. Now you're going to have to buy 100 times of that capacity. And obviously, that's going to come with a high bill. And remember, this bill is incurred every month, right? This is an ongoing expense. You have to keep paying this month to month to month. So yes, this solves the problem, but it incurs a lot of cost. So can caching help us avoid those costs? So that's what we'll be looking at now. So imagine the ISP buys a local cache, which is essentially just a machine that's storing all these objects that are being fetched. And we go back to the previous setting where we are still connected on a 1.54 megabit network. So now, can we actually avoid that original problem and reduce those delays? So remember, the cost of a cache is much smaller, and it's just a one-time investment, right? You buy a machine once and you set it up locally, and that's it, right? So now the question is, how do we even work this out, right? How do we actually mathematically solve this problem? There's something missing here essentially, and that is how many objects can we actually service from the cache. So this is in cache terminology, this is referred to as the hit rate, right? In other words, how many of those 15 requests per second that were going out can be locally serviced from the cache. So in this example, let's just for the sake of argument say the cache hit rate is 40%, which means 40% of those requests can be found locally and they can be serviced locally, which means only 60% of the requests need to be fetched from the origin servers. The other 40% can be serviced locally, right? So based on this information, we can now actually work out the delays, right? So since we are only sending 60% requests out, we would obviously be fetching only 60% of the objects from the origin servers, which means the total capacity, the total traffic we are generating now comes down to 0.9 megabits. And then if you look at the total capacity, the utilization is about 60%. So going back to that picture, 60% would be perhaps just somewhere here. So certainly it's higher than the previous example where we increase the bandwidth, but it's still manageable, right? You're not hit a point where the delays are exponentially increasing yet, right? But remember, this only applies to 60% of the requests. The other 40% of the requests are actually serviced locally, right? So the total average end-to-end delay is 60% of the objects have to be fetched from the origin servers. So in that case, the delay is 2 seconds plus some minor delay here, plus some minor delay here. So what we have done is we've abstracted that to be just 2.01. So just a little more than 2, in other words. And the other 40% of the objects, which are just obtained locally, incur hardly any delay, So we'll just again abstract this to be a few milliseconds because they're just serviced locally, right? So if you do the math here, the average delay is actually just 1.2 seconds. And in fact, this is lower than the delay incurred by increasing the capacity of the link, as we saw earlier. If you go back to the previous slide, the delay was a little over 2 seconds, right? Because each object still needs to be fetched from the origin server. Here, by fetching 40% of the objects locally, we've reduced the delay for those 40% to minuscule. The other 60% still incur that large delay, but then averaging this out, you see the total delay is only 1.2 seconds, right? So by this small upfront cost of installing this cache, we've solved the problem of the delays. We've reduced it to what you would have incurred if you went with a higher bandwidth link, and you have also avoided having to keep paying this monthly additional cost for getting a faster link, right? So this is again just a simple illustration of how caching can work. But again, the only caveat there is having a decent hit rate, right? If your hit rate is very, very low, then there's not a lot of benefit to having the cache there, right? Is the caching typically done at the ISP access link or potentially somewhere outside of your natural traffic path? Well, normally it would be the first hop ISP, right? The resident access ISP that you're connected to. They would set this up, and they would make sure all GET requests are directed to the cache. And then if the object is stored there, it will get serviced there. Is the cache written to concurrently, or does the data go to the cache and then to the client? That's a good question. I guess it depends on how the cache is set up, I guess. I'm not sure of the exact process. It could be either. I mean, it would depend on how the cache actually has been implemented, how the software that's managing the cache is implemented. Where did you get the 1.5? Well, it's just 15 times 110. You're getting 15 requests are going out, 15 responses are coming back, right? And each response is 100 kilobits. So 15 times 100 is 1.5. Okay, I think one of you had asked this question earlier about cache consistency and how does the cache know if the object is fresh, right? So that is certainly an issue, right? Because if you have fetched something and stored it locally here, what if the actual content gets changed, right? Then you have a stale copy of that object. So how do we solve this cache consistency problem? This is again a very classical problem when you're looking at any sort of caches. So there are ways to do that. There's a lot to caching beyond what I'm just covering, but effectively what the proxy will do is, based on certain heuristics, it will go and check with the server if the object has been modified, right? So there's this option here in the HTTP request header, which allows the cache to sort of put in the date. So remember earlier I had shown you the response header, and there was a date where this object was created, essentially the if modified since header in one of those fields. So that's the value that the cache records. So the cache knows that it has stored an object, and this object was created at a particular time, right? So let's say the cache gets a fresh request for this object from one of the local clients. So what the cache can then do is it can go and check with the origin server. Basically, it can send a request with the if modified since header flag, which contains the date. The server can then double check this date against the date for that particular object and check if it has been modified. If it's not modified, it sends back a response saying not modified. If it's modified, then obviously it will send the fresh object, right? Now, of course, having the cache checking this with the server incurs an extra round trip time delay, right, to the server. So certainly this adds an extra delay component. But if the object was not modified, you're certainly still saving a bit of time by not having to transmit the entire object, particularly if the object is very large, right? So there's still some benefit to caching, even if you incur this extra delay from time to time, where the cache has to check with the server if the object was has been modified, right? So yeah, this is actually the header I was referring to. So there's this if modified since value, right? So that can be included. Now, in addition to that, there's also something called an E tag, right? So the if modified since stuff works if it's an object that's static, that's been created and stored on the server. But sometimes you request for stuff that is dynamic. By dynamic, I mean the web server gets a request, then it goes and polls another server, extracts some content, creates the response and sends it back to you, right? So the data that you have requested is dynamically created and sent to you. This can be things like anything that's a bit more dynamic, like sports scores, stock market prices, or anything that you're fetching from a database server, like based on the request you created, right? So in those instances, this day value has no meaning, because this is simply the time the query was generated and that object was created. And that doesn't really tell you, that will obviously change each time you make a request, right? So in those cases, there's something called an E tag that is used, right? So what happens is the server, when it creates your dynamic content, it runs a hash on the actual content of the data that was generated, and it includes that hash in this E tag value, right? And then when your cache is checking for the consistency, it will include this E tag when it sends the request. Then the server can generate that same content. It can generate the same hash, and then it can compare against the value in the request. And if the hash has changed, then it implies the content being requested has also changed, right? So for dynamic content, E tag is used instead of the if modified since value, right? So yeah, this is a way to check cache consistency, essentially, to get over the problem where you might be servicing old data, right? Now, another thing that can benefit content delivery is, of course, replication. So the idea of using web hosting services, where rather than hosting the content yourself, you hand it off to web hosting services, and they will go and place your content on multiple servers around the world. The issues there become then, if you have multiple replicas that are hosting your content, how do you direct the query to the correct content? So there's lots of heuristics on this. It essentially comes down to where the request is coming from. So you'll typically your request would go to servers that are relatively close to you in terms of geography. And also sometimes the load of the servers comes into play, right? And a way to sort of orchestrate all this is through DNS, which we'll be looking at next week, actually, right? And then moving one step further, there's this whole area of content distribution network, right? So there are dedicated companies like Akamai, which are effectively this is their business. So you pay them a fee, and they make sure that your content can be quickly serviced to the end users. So they use all sorts of heuristics to achieve this. So we'll be looking at CDNs in a little more detail next week. So I'll skip this slide for now, and we'll talk a bit more about that a little later. Now, one of you asked about HTTPS. So yeah, I mean, basic HTTP is highly insecure. Everything is sort of sent in plain text. So we all have pretty much migrated to HTTPS these days. So even if you don't explicitly type HTTPS, you'll see that your browser by default is these days using HTTPS, right? And this is effectively, you're still using HTTP. It's just that before So rather than set up a plain vanilla TCP connection, what happens is a TLS connection gets set up between your browser and the server, and then the HTTP request, as we have seen, run over that TLS tunnel effectively, right? Is non-authoritative from the output of the NS lookup is CDN address. We'll talk about that later, Joseph. I don't want to get into DNS now because it's hard to explain that without actually explaining how DNS works. Isn't HTTP vulnerable to packet sniffers? It can be, yeah, exactly. So that's the reason we don't use plain HTTP anymore. Almost all traffic, web traffic these days runs over HTTPS, right? So this ensures bidirectional encryption, which means it's not possible to actually sniff those packets, right? Okay, how are we doing on time? Okay, what I might do is there's a couple of important quizzes I wanted to touch on. So let me halt the content here. I'll start with HTTP2 the next time we meet, but I certainly want to get you to answer a couple of quizzes. So if you could kindly open your browser. And look at this question. Oops, I should activate it, sorry. There we go. So it's kind of revisiting the concepts of non-persistent and persistent HTTP. So this first question is on non-persistent HTTP and no pipelining. So it's saying if you have an HTML page with a base with the index file of size S0 bits and n other objects, each of size S bits, it's assuming that the link has a transmission rate of C bits per second and the round trip time is D. So how long do you think it takes to download this whole website? So this is where drawing that timing diagram will help you, like the one I'd shown you earlier. So essentially the client on one side, the server on the other, and then you work out the delays for the various objects. Let's look at your answers. What's happening? There we go. That's interesting. So let me show you how the delays would map out. Right. So this is assuming we are using non-persistence. Now, of course, to draw this, you would need to assume some value for n. So here I've assumed we've got one base object and we've got two embedded other objects, right? N equals 2. So we first set up the TCP connection, then we obtain the base HTML file, right? So we have D plus S0 by C. At this point, we close the connection, we open a fresh connection. So that's D. We request the first object, another D. The actual time to transmit that object is S by C. we close the connection, open the next connection, fetch the object, and then close the connection, right? So the total delay here would be how much? 1, 2, 3, 4. So essentially it's 2D plus S0 by C plus 2D plus S by C plus 2D plus S by C, right? So effectively this much for the base and then this much for each object, right? In this case, N was 2, so that's 1, that's 2. If you have a third object, you would repeat this, right? So the correct answer would be, going back, I think it would be this one, right? 2D plus S0 by C for the base index page, and then that much for each object, right? So the correct answer would be D in this case. Now let's change things and make this exact same problem. Oh, sorry. But now we are assuming persistent HTTP, but still no pipelining. So the exact same setting, just persistent HTTP, no pipelining. So again, having that, drawing those timing diagrams will help you. Oh, good. So yeah, I agree with most of you here. This would indeed be E and the same logic, right? So in this case, you set up the first connection, get the base HTML, right? And this time you don't close the connection. So which means you don't need to set up a new connection. You can then request the first object, receive the object, request the second object, and so on and so forth, right? So the total delay would indeed be that much to get the index page, and then this much for each of those n objects, right? So well done. Now let's just do very quickly the last one, where we now add pipelining to that. So everything else stays the same. We just now use persistent HTTP with pipelining. Okay, yeah, this is also correct. Most of you have picked the right one. So yeah, this is how it would map out, right? So set up the first TCP connection, get the index. This, I mean, you can't get around this. That delay is kind of constant, whatever you do. Now here you can send the request back to back, and then the responses sort of come back to back. So the delay here would now then be D, and then S by C for each of those objects, right? So that's the reason we get that. So yeah, well done, everyone. I know we went a little over, but it's okay, I guess. So let's call it a day, and then we'll wrap up whatever's left in this slide set, and then we'll talk about DNS when we meet on next Monday. So have a great week. Have fun with the lab, and I'll see you all online or in the lecture next week. Bye-bye.